So far, we know that a negative shear factor displaces points leftwards or downwards. But something else also displaces the points leftwards and downwards. If you look in all the examples, I was careful enough to keep all the figures either above the invariant line. For example, this triangle MNO was above the invariant line, the x-axis, or in front of the invariant line. For example, this triangle ABC was in front of the invariant line, x is equal to 3. Suppose now the figures were below or behind the invariant lines. What would happen if this triangle MNO was below the x-axis, which is the invariant line? Or this triangle ABC was behind the line x is equal to 3. In these cases, we take the perpendicular distance to be negative. We then proceed to multiply with the shear factor and get the displacement. For example, draw the image of triangle PQR under a shear factor 2 with x-axis invariant. Let's start with P. Perpendicular distance will be minus 4. S will be 2. Displacement is minus 4 times 2, giving us minus 8. So we move 8 units leftwards. This is P prime. Point Q, perpendicular distance from the invariant line is negative 1. S is 2. Displacement is minus 1 times 2, giving us minus 2. So we move 2 units leftwards. Point R, perpendicular distance is minus 1 units. S is 2 and displacement will be minus 1 times 2, giving us minus 2. So we move 2 units leftwards. This is the transformed figure. Another example, map the image of triangle XYZ under a shear factor 3 with x is equal to 8 invariant. We start with point X. Perpendicular distance from the invariant line is negative 1. S is 3. Displacement is minus 1 times 3, giving us minus 3. So we move 3 units downwards. Point Y, perpendicular distance from the invariant line is minus 2 units. S is 3. Displacement is minus 6. That is minus 2 times 3. So we move 6 units downwards. Point Z, perpendicular distance is negative 3 units. S is 3. So displacement is minus 3 times 3, giving us minus 9. So we move 9 units downwards. This is the image. Now, this understanding is important when dealing with cases where the invariant line passes through the figure itself. Consider this example. Rectangle ABCD is to be mapped under a shear factor 2 with the line x is equal to 3 invariant. Notice that points A and D are behind the invariant line, while B and C are in front of the invariant line. Attempt on your own to map the image by following what we've done. Expect an image with one side displaced upwards and the other side downwards. Good luck. Next transformation, stretches. Now consider a spring fixed onto a red surface. If the spring is pulled, it stretches out. When pushed, it compresses back. However, in either cases, the red surface does not move. It is an invariant line. Notice that all the other points on the spring move perpendicular to the invariant line. This is a stretch, a transformation that keeps one line invariant and all the other points move perpendicular to the invariant line. So in a stretch, displacement is perpendicular to the invariant line. Points on the invariant line are also invariant. The stretch factor M is given by image distance from the invariant line over the object distance from the invariant line. So given M and the figure, you can calculate the image distance. That is, image distance is equal to M times the object distance. Note that all distances are measured from the invariant line. For example, map triangle PQR under a stretch factor 2 and y-axis invariant. Let's start with P. Object distance from the invariant line is 2 units. M is equal to 2, and therefore the image distance will be 2 times 2, which is 4. So the point moves 4 units from the invariant line to the right. Point Q. Object distance is 4 units from the invariant line. M is 2. Image distance is given by 4 times 2, which is 8. The point will therefore move 8 units to the right from the invariant line. Finally, point R. Object distance from the invariant line is 3 units. M is 2. Image distance will be given by 3 times 2, which is 6. And so the point moves 6 units to the right from the invariant line. And there is our image. What if we transform the triangle by stretch factor -2 with the x-axis invariant? Negative means the stretch is downwards or leftwards. In this case, it will be downwards. Point P. Distance from the invariant line is 1 unit. M is -2, so image distance will be -2 times 1, giving us -2. So we move 2 units downwards. This is P prime. Point Q. Distance from the invariant line is 1 unit. M is -2. Image distance is -2 times 1, giving us -2. So again 2 units downwards. Finally, point R. Distance from the invariant line is 3 units. M is -2. Image distance -2 times 3 is -6. So we move 6 units downwards. This is R prime. So P prime, Q prime, R prime is the image of triangle PQR under a stretch factor -2 with the x-axis invariant. Now, just like in shears, when the object is below or behind the invariant line, the object distance is negative. An object can also undergo a two-way stretch, which is a combination of 2 successive stretches, one after the other. For instance, consider the square ABCD. Let it undergo a stretch factor 2 with x-axis invariant, and then a stretch factor 3 with y-axis invariant. Let us do the first stretch, x-axis invariant. In this case, the image is below the invariant line, and so the object distances are negative. Also, points A and D lie on the invariant line, and so they won't change. Point B. Distance from the invariant line is -3. M is 2, so image distance is -3 times 2, which is -6. So we move 6 units downwards. Point C. Distance from the invariant line is -3. M is 2. Image distance will be -3 times 2, which is -6. So again we move 6 units downwards. So we have our B prime, C prime. Now, this new figure is to undergo the second stretch with the y-axis invariant. In this case, the figure is in front of the invariant line, and so the object distances will be positive. Also, points C and D will be invariant. A and B will change. Point A, object distance is 3 units. M is 3 in this case. Image distance, 3 times 3 is 9. So we move 9 units to the right. Point B, object distance is 3 units, M is 3, image distance is 3 times 3, which is 9. So again we move 9 units to the right, and this is the final image of the 2 successive stretches. Always remember that shears move points parallel to the invariant line, while stretches move points perpendicular to the invariant line. Next, transformation matrices. Now, when it is not mandatory, it is easier to transform figures through calculations rather than constructions. Matrices provide an easier way of working out the coordinates of points on the image after a transformation in certain special cases. Let's see that. Consider a unit square OIJK on the Cartesian plane. If you take the points I and j and write their coordinates in vector form, I is equal to 1, 0 and j is equal to 0, 1. If you combine the two, you form a matrix 1, 0, 0, 1. This is what we call an identity matrix. Using these 2 points I and j, we can always form a 2 by 2 matrix for a given transformation. Take an example, a shear transformation. Suppose we want a shear matrix for scale factor 2 with y-axis invariant. We go to the unit square and consider points I and j and subject them through that transformation. In this case, point j will be invariant because it lies on the invariant line, so its coordinates remain j prime 0, 1. How about I? In shear, a point moves parallel to the invariant line, so displacement is equal to perpendicular distance from the invariant line times s, the shear factor. In this case, we shall have 1 times 2, which is 2. And so point I will move 2 units upwards. The new coordinates will be I prime 1, 2. If you write I prime and j prime as column vectors, I prime will be equal to 1, 2 and j prime is 0, 1. As a matrix, you shall have 1, 0, 2, 1. This is the shear matrix for the scale factor of 2 with y-axis invariant. Given any coordinates, you simply multiply with this matrix to obtain the coordinates of the image. In this matrix, 2 is the scale factor. If the scale factor was 3, the shear matrix with y-axis invariant would be 1, 0, 3, 1. So in general, the bottom 0 of the identity matrix is replaced by the scale factor when the y-axis is invariant. And so the shear matrix with y-axis invariant is 1, 0, S1, where S is the shear factor. If you repeat the process with x-axis now invariant, you will find that point I will be invariant and that j will have new coordinates 2, 1. So the shear matrix when x-axis is invariant will be 1s, 0, 1, where s is the shear factor. For example, triangle ABC with coordinates A, 1, 1, B, 3, 1, and C, 2, 4 undergoes a shear transformation with x-axis invariant and shear factor -3. Write the coordinates of the image. If you don't have the transformation matrix for this shear, you simply draw a unit square and subject I and j to the transformation. It will give you the matrix. In this case, the matrix will be 1s, 0, 1. S in our case is -3, and so the matrix is 1 minus 3, 0, 1. We multiply each point on the triangle with this matrix. Point A, 1, 1, so we have 1 minus 3, 0, 1 times 1, 1. 1 times 1 plus minus 3 times 1 is -2. 0 times 1 plus